Now we can figure out R1. It'll be 20 volts divided by 160 milliamps. Which would be 125 ohms. Did you get that, Z?
Yeah, that one was a little easier. That was pretty easy.
Okay, and then we could also calculate power right now too, because we know our total current is 160 milliamps, and we still have a voltage of 100 volts, so it'll be 160 milliamps times 100 volts. Is that 1.6 watts? Or 16 watts?
Yeah, 16. Yeah.
Okay. So, any question about those guys? Let me see, do we have any more on that page? 1, 2, 3, 4, 6. Did we do 6? Yeah, we just did 6. Okay. How about the problems on 134? We had 2 of those. Let's do one of those. So, page 134, number 7, yeah. Okay, it says, discuss the results of shorting out R2 in figure 511 when the power ratings of R1, R2, and R3 are 25, 50, and 25 watts, respectively. And that's figure 511. Okay, where in the heck is figure 511? All right, let's go find figure 511.
Yeah, that's 541. That must be way back.
Yeah, okay. 511. Oh, here we go, right here.
I didn't see it. What page is that on?
It's on page 110.
Oh, 110. Oh, yeah, it's way back there.
Okay, let's figure it out here, right? We got 2 resistors, and we're going to short out R2. Okay, so here we go. If we short out R2, right now our total resistance would be R1 plus R2 plus R3, correct? If we short out R2, then our total resistance is basically R1 plus R3. So in which case our total resistance would be 80 ohms, right?
80 ohms, yeah.
Okay, so if we have 80 ohms, our total current, if we have 90 volts, is going to be 90 divided by 80, right? Or 1.125 amps. Okay, so let's figure out how much power is R1 going to consume with that much current. Remember, power is I squared times R. So if we squared it, matter of fact, I'm going to store 1.125. Well, first I'm going to square it because I'm going to use it again. So when we square 1.125, you come up with 1.265. Let me store that number. So to figure out how much power R3 is consuming, you multiply that 1.65, which is the square of the current, times 35. He's consuming 44.2968. Right. Okay, that's what R1 is consuming. Now R5 is consuming that same current, the 1.265, which is the square of the current, times 45 ohms. He's at 56.953 watts. Okay, so let's go back to the problem here.
Yeah, what's the problem say?
It says okay. Says discuss the results of shorting out R2 in figure 511 when the power ratings for R1, R2, and R3 are 25 watts, 50 watts, and 25 watts respectively. Okay, we calculated that R1, once we short it out, it's going to be drawing 44 watts, right?
44, yeah, 44.29.
Yeah, and his power rating is only 25 watts. So his power rating is 25 watts, and he's pulling 44 watts now. R3 has a rating of 25 watts, and he's pulling 56.
Yeah, no, I think it was 65, wasn't it?
Was it 65? I got 56. Let me see.
Oh, was it? Oh.
It was 45 ohms times 1.265. I got 56,953.
Oh, maybe it was 56, yeah.
Yeah, either way, he's only rated at 25 watts. And he's at maximum power, so what's going to happen is, when resistors...
1.265?
Yeah, 1.265.
Times 45?
Yes.
Yeah, 56.92, yeah.
Yeah. So what happens is,
okay.
The wattage rated on resistors refers to how much heat they can dissipate. Okay? So at this point, this resistor can no longer dissipate the amount of heat it's generating, so he's basically going to heat up and burn up. Okay? And usually what would happen is you'd have a fuse, so because the current went up, and the fuse would open, would blow, and it would stop the current. Because fuses protect from overcurrent. So when something shorts out, it means you have a low resistance, which means current's going to increase, and the fuse needs to blow. If the fuse did not blow, then R1 and R3 would probably burn up.
Okay.
Cool. Let's move into the other homework. You know, I went on vacation this weekend on Friday. So I had all this homework done Thursday night, and I was at home, and I scanned it on my scanner at home, tried to email them, but it wouldn't go through the firewall. And so I tried, and I couldn't get it through there, so that's why I sent it in on Monday. That's when I came back to work. So apparently if you scan from a company scanner, it accepts the PDFs, but it wouldn't from my home one. Okay. Let's work this problem here. First of all, do we need to work this first problem? Or you guys got that pretty well down?
Yeah, I haven't even got a chance to look at it yet. Like I said, I just got back from vacation.
Okay, that's cool. Well, let's work it anyway. Okay? So what we have here is, we got a combination circuit, okay? R1 is in series with the combination of R2 and R3. So it says R1 is 100 ohms, R2 is 600 ohms, R3 is 400 ohms, and total voltage is 34 volts. So we need to find everything else. So first thing I would do in this point is figure out my total resistance. Now, how am I going to do this so you can see? Okay, so total resistance equals R1 plus 1 over R2 plus 1 over R3, right? Something like that. And so RT should equal 600. I got 340 ohms. Okay. Yep. Okay. 340 ohms. Cool. That's RT. Now, if RT is 340 ohms, IT will equals VT over RT, which is 34 volts over 340 ohms, because we gave you the voltage right here. So 34 divided by 340 is 100 milliamps, is total current, IT. So if we have, we got 100 milliamps going through R1, and R1 is 100 ohms. R1 is going to drop 10
For
volts.
R2 and R3, you got 340?
I got 240.
Okay. Because you wrote 340, so
What?
you just plus the other 100, right?
Yeah, so you just plus that 100.
Okay.
Yeah. Here's
Okay,
the.
okay, I'm looking now.
Yeah. Okay. Cool. So now, say again. Okay. So we know if we have a total current of 100 milliamps, and we know R1 is 100 ohms, we can figure out the voltage drop across R1 is 100 milliamps times 100 ohms, which gives us 10 volts. Okay, so we have 10 volts dropped across R1, which means the voltage drop across R2 and R3 will be our source voltage, which is 34 minus 10, so it will be 24 volts across R2 and R3.
Hey, Jim, one thing.
Say again?
Yeah, I missed how you came up with 100 milliamps.
Okay. Okay. I got 100 milliamps. Remember, our total current equals our total voltage divided by our total resistance, right?
Right.
So our total voltage is 34 volts, and our total resistance, which we calculated, is 340 ohms.
Right.
So 34, 100 milliamps.
Gotcha. Yeah, sorry, I didn't see the voltage still there.
Okay. So you see how we got the 10 volts across R1 now, right?
Yeah.
Okay. So now if R1 is dropping 10 volts and our source voltage is 34, then the voltage across R2 and R3 have to be 24 volts.
Because that's the voltage.
Right, because they have to add up, right? Kirchhoff. So now that we know the voltage across R2 and R3, we can figure out the current through R2 and R3. So it would be, the current through R2 would be 24 volts divided by, R2 is 600 ohms, and current through R3 would be 24 volts divided by 400 ohms. And the sum of these should equal 100 milliamps total, right?
100 milliamps total, yeah.
So 24 divided by 600, I have 40 milliamps, and 24 divided by 400 gives me 60. 60 plus 40 equals our total current. Is that making sense for everybody?
Yeah.
Okay. That was an easy one. Yeah, that's the first one. Okay, let's move on to the second one. Are you guys ready to move on to the second one? Okay. The second one says... Oh, the second one's a little tricky here. Huh. You can almost see both pages. Okay, the second one, we have I just use this. Second one, we have a total voltage of 120 volts. What is that? I through R1 equals 6.1935 milliamps. R2 equals 25K. And the voltage across R3 equals 58.065 volts. Woo! Okay, so let's see here. Okay, we know that IR1 is also IT, right? All the current goes through R1. Right? Somebody nod. Okay. Okay, we also know that VR3 is going to be the same as VR2. So the voltage across R2 equals 58.065 volts. So we can figure out the current through R2, which would be 58.065 volts divided by 25K. So I got a current through R2 at
2.32 milliamps.
Yep, 2.32 milliamps. Okay?